Yeah, I'm going to do that right now to make it a presenter. All right. Yeah, it looks like I see your name now. I'll make you the presenter, and then I'll log in on another machine just so I can see what it looks like to other guests, and if there's any problems, we can check back in by cell phone. All right. Okay, great. Talk to you soon. Bye-bye.
Hey, Rogelio, I'm logged in now.
Okay. Can you share your screen?
Yeah, just give me like 2 minutes if you don't mind.
Okay, that's fine.
Thank you. Oh, well, okay, I'll be online, yes. Can you see me now?
Yep, I see your screen. Can you maximize it? And put it in presentation mode?
Yeah, I did. Oh, are you seeing something?
I'm seeing it in a window. Maybe that's just on my screen. Okay, now it's full screen.
Okay. I'm going to take this off for a minute if you don't mind.
No, we still have time. We have 10 minutes.
Okay, thanks. Yes.
Yep.
So you'll just see my browser window right now. Are you
Yeah,
seeing the browser?
no problem.
Okay, yeah, just if you give me a few minutes, I'll just.
Sure.
Okay. people do not have access to the best epi wafers out there because, they may be making materials themselves. Fabrication equipment, it is a state-of-the-art, fully automated 25,000 wafers a month, class 10 CMOS line. I think it's more like 35,000 wafers per month. And if you notice in the history of, semiconductor processing, when things went from 4-inch to 6-inch, there was a significant change in terms of the automation level in foundries. Quality standards, the foundry adheres to the PS 16949 and the newer automotive standards for over 14 years, whereas 4-inch foundries have to struggle to meet those standards. Cost structure, it's obvious that 6-inch wafers offers 2.25 times the number of devices that a 4-inch wafers offers, so the long-term cost structure of this platform is better than 4-inch wafers. And then this is an important aspect about process innovations. There are a whole lot of issues that were solved by silicon folks which don't have to be reinvented. So it is, we believe, a strong advantage that because of many things that were learned by the silicon people can be applicable and are being applied to silicon carbide processing now, where there is a foundry model rather than everything being captive. So I'm going to talk now about the two major product categories. This is our transistor and our diode product proposition. So in terms of silicon carbide MOSFETs, we endeavor to offer the lowest RDSon MOSFETs, which would have fast and temperature-independent switching, good avalanche ruggedness, high reliability, good short-circuit capability, and low costs at high volumes. So, we want to be able to offer devices which are a good match and balance of all these important aspects that make a successful device in the market. Our silicon carbide Schottky MPS rectifiers offer low on-state voltage drop, zero reverse recovery, low leakage currents, and frankly, many competitors are also offering these three very core aspects of Schottky diodes. However, we like to distinguish ourselves by offering also very high surge current capability, a high avalanche rating, and also good high temperature capability. And we have certain packaged devices in small footprints, and again, we intend to offer these devices at high volumes at low cost. This actually, slide 6 shows us the product portfolio. At our 1200 volt node, this is the sweet spot for most of GeneSic's products. We are concentrating more on the higher voltage side, and as you can see, we offer one of the most widest offering at the 1200 volt silicon carbide Schottky rectifiers, from 1 amp to 200 amperes in various different packages. The items in red are our previous generation devices, but the MPS series is the new series of our Schottky diodes. We also have few 650, 1700 volts, and 3300 volt silicon carbide Schottky diodes on the market, and this slide just shows you some of those offerings. We've been offering 3300 volt diodes since 2012 through our major distributors, which are Arrow, Newer, Mauser, DigiKey. So our products have been available through these major worldwide distributors since 2010, 2012 timeframe. And more recently, our 1700 volt offerings, which is shown below, from 5 amp to 50 amps, are also very gaining very strong traction amongst industrial markets. So let me now go into a bit of science of how we make, how we distinguish ourselves. So we do design our Schottky diodes, these MPS series diodes, with a view to offer very high surge currents. And the reason why we do this is because there is a strong market demand for light industrial and industrial markets where these diodes need to have high surge currents, because very often these diodes are used in either capacitor charging situations or when during the initial startup of a circuit, it has the diode charges up a capacitor and a big surge of current goes through the diode. And so how do you look at a diode which has a high surge current? Well, if you just took a standard diode and measured it up to fairly high current levels at different temperatures, you will see that initially it behaves like a Schottky diode, like I'm showing on my mouse here. But at high current, the current goes, exponentially and not linearly, as a Schottky physics would say. Now, this is a higher current device, but we wanted to benchmark our products with vendors, so we chose 1200 volt 10 amp device samples from many different vendors. So you can see the green one is the GeneSiC device, and then we have vendors A through H here, where we tested their IV characteristics, and you can see these IV characteristics versus drain current. So just to calibrate, these are 10 amp devices, 10 amp rated devices from various manufacturers, and we are testing them up to 120 amperes or so under pulse conditions and at high temperatures, 175 degrees C. Now, to measure the limits to which you can take these surge currents, you have to also, you should try to measure the voltage drop across the device if you want to properly understand and make good models to improve these devices. So on the right, we see some surge current measurements that were done on our 1200 volt 10 amp devices with successively increasing current levels from 75 amps, then to 110 amps, to 135 amps, and finally 160 amps. We also measured the voltage drop across the diodes, and this helped us make a good model for our diodes. So, as I mentioned, at high currents, these merged PIN diodes show PIN-like characteristics in contrast to Schottky-like characteristics, and we've developed very good thermal models for these devices. So, we of course test these devices to failure in order to see what is the ultimate limit, and we decapped devices and see what is the mechanism of the failure. And what we found here is a photomicrograph of a diode which went through surge failure. Essentially, the aluminum melted. And when we do an electrothermal simulation, and this was presented in some papers that we published in the last 1 year, we see that the temperature exceeded 650 degrees C, at which point aluminum melts. But we are quite happy to report that we think we have a very good idea about the modeling required for such behavior. On the right side, we show you the surge current, the maximum surge current that is measured on devices from GeneSiC and from our competitors. And one thing I should mention that the surge current decreases slightly as you increase the temperature from 25 degrees C to 150 C. So you can see that at room temperature, 25 C, our 10 amp device went a little over 160 amps before it failed for a 10 millisecond pulse, and at 150 C lower. And that has been seen consistently from many of our competitors also. Another competitor showed pretty good results here, vendor D, but there are some which are really not very acceptable, frankly, from the market standpoint. So we believe that, the surge current is an important aspect for these diodes. This is getting to the next level of maturity for these diodes. And again, I should mention that all of our silicon carbide Schottky diodes are now being produced 6-inch foundry. So these results are actually from diodes made on 6-inch platform. So the other aspect that is also a distinguishing factor is the avalanche ruggedness. So in avalanche ruggedness, essentially it's a measure of once you put a device under a voltage that is higher than its breakdown voltage, how much energy can it take before it blows up? And this is, on the left you see the drain voltage and diode current and time versus time, and you can see that the typical pulse is initially a high current or the rated current is flowing through the device, and then it goes into an avalanche condition because you charged up an inductor and open circuited it, and you go through an avalanche breakdown of the diode. And you can see that in this case, this is a 1200 volt 10 amp rated device, which actually broke down at about 1600 volts. And we see a relatively stable or to a positive flat top here, and the integration of these current and voltages gives us the energy, the avalanche energy, or we can also call it UIS energy of these diodes. And again, we did compare GeneSiC diode to all the other vendors in the market, and we offer a pretty high avalanche energy. We also measured the avalanche voltage at which we are failing, and these are random samples. There was nothing that was picked up in particular, and each of these points actually refers to 3 samples, average of 3 samples. So you can see that, yeah, and by the way, that was also true for our surge study. So you can see that we offer 295. There are some other vendors who offer higher. There are some vendors who offer really high levels of avalanche ruggedness. But that's because they also have higher voltages at which they break down. Same inductors were used, and we could see that while we are not the best, we are amongst the high achievers on the avalanche ruggedness scale. One other thing I wanted to mention here is that we worked hard for many years on making high temperature Schottky diodes. In fact, previously we used to have a separate line of high temperature Schottky diodes. And those learnings have helped us to achieve low leakage currents even on our standard offerings in Schottky diodes. And that is what is shown on this curve on the right here. Our reverse leakage currents up to 1200 volts from room temperature to 175 C. Our diodes are roughly within 3 or 4 0.2 to 0.3 microamps at 1200 volts at room temperature. And even at 175 C at 1200 volts, you can see that the leakage currents are not more than 10 microamps or so. They're more like 7, 8 microamps. And we find that to be an important advantage we have. This is showing GeneSiC versus 3 other vendors. You can see an order of magnitude lower reverse leakage currents have been measured. In terms of on voltage drop, also we have done optimizations. These are the same devices, not different devices. So while we are getting low leakage currents, we are also getting reasonably low VF at high temperatures. So these are measurements done at 175 C, 3 of our samples and 3 of samples from each of these vendors. And you can see that at high temperatures we are relatively low. Also, an important aspect of devices is the thermal resistance that the package, the total package device has, because that ultimately depends on how much current you can put through the device, even for a given area even. So, for example, having a low thermal resistance can be looked upon as either you can put more current through the same device or you can run the device cooler. In either situations, it helps in terms of both performance and long-term reliability of these devices. So we have actually made direct thermal measurements of 1200 volt 10 amp devices, and we are happy to show a lower thermal resistance by a fairly significant amount. That is because of some innovations that we have done on our chip and packaging technologies. And again, this is applicable to all the diodes, the MPS series diodes we have. Lower capacitance yes, at some point when the switching is quite fast, you do see that device capacitance becomes important. And so even though the Schottky diode switching times are very, very small, you know, some people are exploiting the high speeds to the next level, and for that, having a low capacitance is a very important aspect of it. And we measure our capacitances versus voltages. So, you know, most of the time the zero bias or 1 volt reverse bias capacitance is an important number. And here we plot 3 of our samples versus our competitor samples, and we see roughly similar numbers, although somewhat lower capacitance numbers as compared to some of our competitors. So that's about diodes. I'm going to talk next about our efforts into silicon carbide MOSFETs. We have chosen a relatively standard DMOSFET for making our MOSFET product line, and we believe this design offers a highly uniform production and affords high yields, as well as a good balance of robust and reliable performance. So overall, we strive to achieve low drain source resistance, low gate charge by offering low input and output capacitances, robust design for high avalanche ruggedness, low conduction losses at high temperatures, having an intrinsic diode with low reverse recovery charge, and again, low cost at high volumes for these devices. Our MOSFET roadmap, again, these devices have not yet been released, but they are very actively being worked on. We intend to offer them at the popular nodes, and those are at 1200 volts and 1700 volt MOSFETs, going from 280 milliohms down to 25 milliohms for 1200 volt devices, and 1000 milliohms and 45 milliohms for 1700 volt devices. And these are the packages, the TO247s, 4-leaded, 3-leaded, and a D-square package with a 7-lead Kelvin connection, which is quite popular at this moment. And we intend to, we had actually offered our silicon carbide junction transistors previously with this package dating back to 2014-15 timeframe, but we intend to use the same package, this package for our MOSFETs as well. We also have a strong commercialization desire to go after the 3300 volt node. Again, we have made 350 milliohms and 40 milliohm MOSFETs, and although 40 milliohm MOSFETs are primarily targeted towards module applications, but you know, it might take us some time before we can get the expertise in the module side of things. So we intend to actually offer them in a surface mount TO268 package for people to play with, and also there are actually applications that are quite compelling for these devices. 350 milliohms in a D-square pack is also, we've actually already sampled it to a few customers. So I'm going to talk not about the lower voltage, which is 1200 volts to 1700 volt devices. I'm going to rather talk about our efforts on the higher voltage MOSFETs. And we have made some 4500 volts MOSFETs, and these are the characteristics of the 4500 volt MOSFETs. You can see the RDSon is quite near theoretical for the kind of epitaxial structures we had used, 35 microns 315, and we were able to get a fairly high breakdown voltage of 4600 volts on these devices. And we wanted to first study how exactly to design and what kind of parameters are important to have a fundamentally good device. And And one of the aspects is that you want to make sure that the breakdown voltage is well behaved. And what I mean by that is that if you measure the reverse IV characteristics, it should have a low leakage currents, and this is the floor of our leakage current measurement system, all the way up to 4,600 volts. And as you increase the temperature from 25 degrees C to 100 degrees C, we find that the breakdown voltage increases with temperature. And that's important because that shows that you are actually fully utilizing the benefits of the silicon carbide material and not limited by some design or other aspects or defects and so on. So when we plot our breakdown voltage versus junction temperature, we find a fairly good slope of 1.33 volts per degree C, which is an important aspect for how well we design these devices. In terms of the RDSon, I wanted to point out that these devices, when they go from room temperature to 425 C, they very closely follow the RDSon formula for the mobility, and hence we find that for these high voltage devices, we are able to exploit the true nature of the silicon carbide and not be limited by the channel resistance. So its on resistance is solely determined by the N- drift layer properties. One other aspect which is kind of interesting and important to understand is that if you plot the MOSFET on resistance versus the gate source voltage, there's a debate of whether it should be 20 volts or 15 volts and so on. And at room temperature, yes, you do see some difference in the RDSon penalty you would pay for going after 15 volts, for example, versus 20 volts. But at higher temperatures, where most often these devices are being used, like 125 C or 150 C, the reduction in RDSon between 15 volts and 20 volts is quite minimal. For example, here we show that between 25 C and 150 C, the RDSon difference while it was 13.2%, it's only 2% at 150 degrees C. We also are finding that very often end users are using power MOSFETs as a in the synchronous rectification mode, where under negative drain bias, they want to use the conduction of the MOSFET in the third quadrant. And this has been rather difficult to achieve for many MOSFET manufacturers due to various reasons, mainly threshold control and so on. But we find experimentally, we show experimentally very good third quadrant operation. We see at zero bias, we see a pretty distinct diode characteristics, and as we increase the gate bias, we are seeing a linear IV characteristics here. And this is also true for high temperature operation. You can see even at 150 C, we do have a bit of a knee here, so we are able to block the MOSFET under zero bias and have it be fully conducting at 20 volts or 15 volts or so. Now, let me talk a bit more about the short circuit behavior. Short circuit behavior is a very hot topic for the last couple of years on MOSFETs, and we've done a systematic study on how the design parameters and other factors affect the short circuit behavior of MOSFETs, and we have published this, I think, already, some aspects, and I'm not going to go into all of them, but the way short circuit, the mode of short circuit that we are showing you results for is that you take the device, and unfortunately it is difficult for us to apply more than 2,000 volts for these 4,500 volt devices or so, and then you just turn on the gate across the device, and the current shoots pretty high, and then we turn it off with the application of gate bias, and successively we increase it from first 2 microseconds to 3, 4, and plot the drain current as we are increasing circuit time. And we use many of these measurements to also develop a good electrothermal model for our MOSFETs in order to see, if we can somehow understand and predict the mechanism of short circuit for our MOSFETs. And as a result of that electrothermal model we show on the right, the simulated junction temperature and also the short circuit withstand time versus peak drain current in amperes. And you can see that the simulated curve shows very high temperatures are reached under, the short circuit conditions, even up to 1800 degrees C somewhere in the junction. And of course, that corresponds also to a reduced short circuit withstand time here. So the other thing one can say is that, in this case, this was only a 350 milliohm, or you can say, let's say, 10 amp device, but we were passing, 50 amperes through it and still be able to get 8 microseconds on this device. Now, we wanted to also see, we had different designs. By that, I mean different channel lengths, different JFET gaps, different JFET dopings, and we wanted to see how this various designs affect the short circuit capability. And we also wanted to find out what is the impact of gate voltage on the short circuit times and energies. And that is what is shown in these graphs here. The graph on the left shows the impact of gate bias. Instead of 20 volts, we looked at 20 volts, 18 volts, and 16 volts, and see that you can actually increase the short circuit time by reducing the gate bias. And this has been done by one other researcher that we know of. Probably others have also done it. And also, we wanted to see short circuit failure pulse for different designs of our devices. So these are different designs, D1 through D4. And based on this, we have been able to get more insights into how to design devices with good short circuit capability. We also wanted to do a study on how, after many of these short circuit pulses, and we use 10,000 pulses, how does the device characteristics change? Because, you can say, yeah, we put some short circuit and the device is fine, but, it's important to show the experimental data on that as well. And these curves actually show how, after the impact of 10,000 pulses, how does the IV characteristics change? In our case, we did not see any difference between at 20 volts, 15 volts, at 10 volts, you start seeing some differences before and after. We also see the transfer characteristics versus gate, how pre-test what was the device. And we do see that actually the threshold voltage increased slightly, especially as you increase the short circuit time. And that's somewhat insightful. Gate currents also are not found to change much with the short circuit pulse in our case, while we were keeping everything within the bounds. So you can see that gate oxide or gate leakage current was not really affected. I'm going to next talk about the avalanche measurements we have done on our 4600 volt MOSFETs. And again, this got mixed up here. On the left, we are still talking about the short circuit case where we are doing different gate biases and the various pulses. But on the right, we talk about the UIS capability. We used this MOSFET to do avalanche measurements similar to what I showed on the MOSFET, on the diode case. However, considering that these devices were 4500 volts, they actually break down at close to 5000 volts. And you can see that we are able to get a pretty high avalanche energy of close to a joule at 5,000 volts for these devices, relatively small devices. So finally, I will say that GeneSiC, strives to provide industry's most detailed and accurate data sheets. Believe it or not, it's important. Many a times there are errors that we find in data sheets, and also that leads to a lot of confusion and so on. We also provide detailed and accurate LT-SPICE models for all of our products. We have done enormous amount of work internally to try to get to support our customers to have these kind of models. And there is a lot of work that still needs to be done on this aspect, because silicon carbide MOSFETs are particularly complicated in terms of modeling because of the way channel design is happening. Similarly, diodes are also not that easy because of these surge current and avalanche characteristics that are becoming more and more important for end-use customers. Often we use, we help our customers by taking their designs and doing LT-SPICE models on request. We made a lot of boards, like gate driver boards and evaluation boards, and we strive to give these as much as possible to our end customers and also to our collaborators and so on. And we do offer also customized packaging for our products and so on. So lastly, I wanted to thank our supporters. We wouldn't be nowhere near where we are right now without the support of our sponsors like PowerAmerica and the Office of Naval Research and Department of Energy SBIR program, and many others. I apologize for not mentioning others who have supported us for a long time. And I also wanted to thank XFAB, John Ransom's team. We have worked very strongly with them over the last 3 years, or more than 3 years now. And there's a lot of hard work that, everybody's coming to speed on that. So it has helped us produce state-of-the-art products for our customers. And also we are looking forward to, one message I want to send out is we're looking forward to collaborations, both with universities as well as with our other members who are supported by PowerAmerica and overall ecosystem for silicon carbide adoption. So thank you very much for your attention. I can certainly take some questions.
Thank you very much, Ranbir. That was a really good presentation and very good points made. And I want to jump right to the questions because we do have a few already that people have typed into the chat window. So I'll read those out. And again, if you have any questions, please select the chat function at the top of your screen and type your questions, and we'll get to them all in the order in which they're submitted. So the first question is, given that power loss in blocking condition for diodes is much lower than that in forward condition, what limits do you use to design the high temperature leakage of your devices? So,
yeah, that's a good observation, and many of our competitors are ignoring the need for low leakage currents. However, we believe that to specify a criteria for this is, yes, as the person who asked the question has identified, this is a difficult one to gather. And once you talk to a wide range of your end customers, you have to then find out, where is the compromise between serving a particular customer for low leakage versus, a large number of customers who haven't asked that question. We believe fundamentally that offering low leakage currents, and again, leakage current increases with temperature, and that's what really limits the high temperature use of, for example, silicon devices. Very often, offering low leakage currents is important from a fundamental device design and fabrication standpoint, but also as things are moving towards low standby energy loss environment, there's a whole lot of Energy Star regulations. There are other sort of requirements that are they are making components to not dissipate too much energy while the system is under standby or under off condition, for example. We believe this will become more and more appreciated as these devices proliferate. So what criteria to use? Yeah, you know, at some point you have to figure out how much other parameters on the diode are being affected by the leakage currents, meaning, you know, what is the optimum design point there, and you choose the one where you don't compromise much and yet offer a low leakage current. So, yeah, all I can say is the design point has to be chosen such that you can still offer low leakage currents while not affecting other parameters.
Okay, thank you. The next question is the device designed for improving 10 microsecond surge different from the design for improving 10 millisecond surge? You showed data for 10 millisecond surge. Do you also have comparisons at 10 microsecond level?
Yes, that is also a difficult question for me to answer because the equipment that you need in order to measure 10 microsecond is quite involved. It's quite different and difficult as compared to 10 milliseconds. From a fundamental design standpoint, and actually it's meant for different, so different people ask for 10 millisecond, and which is basically just inrush currents through diodes when they are doing charging applications. And 10 microseconds are often asked by people sometimes who are doing some pulse applications and so on. So in terms of 10 milliseconds, there is an impact of the thermal design of the device and package that affects 10 milliseconds to some extent, whereas in 10 microseconds, the thermal design is not really important. Have you been able to distinguish the 10 millisecond versus 10 microsecond in terms of design? I do not believe so. I don't think we have looked into it in as much detail as you know, we will, that you've asked the question.
Thank you. The next question is, do you see a need for super junction structure or trench gate with silicon carbide MOSFETs?
I would say that if your consideration is low RDSon and also having a higher transconductance, you know, those kind of structures, trench structures, and superjunction structures may offer benefits. However, there are a whole lot of, you know, production issues, basically manufacturability issues, we believe, for both of those structures. And also, there are other compromises that you have to make. For example, in superjunction, the output capacitances can be very high, and most people are now quite used to using silicon carbide MOSFETs, and the high output capacitance will probably not be very easily will not be palatable to them anymore. For trench structures, we believe that it requires a whole new mindset in terms of production capacity and capabilities. Whether they offer a better rugged solution or not, that is a big debatable question. I think certainly for most designs, trench structures will suffer from short circuit capability limitations, and also from possibly avalanche ratings as compared to the conventional structure. So, yeah, I would say that I would not discount them completely. However, the state at which the silicon carbide devices are in production and in the marketplace at this moment, we believe that you know, a standard MOSFET offers the best of all worlds as it looks right now.
Okay, next question. Why use such small packages for 3300 volt devices, both diode and MOSFET? And how do you meet the creepage requirements for high voltage?
We make these small diode packages and also MOSFET packages because the customers ask us to. Yes, I do agree, they do defy the creepage requirements that are imposed upon typical PCB design guidelines. However, we have found, and again, these small packages we have been selling, like the SMB package, we've been selling since, like I mentioned, 2012, or even the 3300 volt diodes. And there are some tricks that our customers play in order to help in terms of creepage and also the design that they put it on. Very often these devices are used because they offer industry's lowest inductances. So now silicon carbide offers so much high speed that, you know, people are not able to find a good package for it. And this package actually offers very low inductance, lowest induction as compared inductance as compared to any other package. So what do we suggest to our customers? Not much, unfortunately. I don't know how, but they do figure out, well, actually, I do know how, but they have figured out ways to mitigate those creepage issues.
Okay, the next question is, can the body diode of 4600 volt silicon carbide MOSFET be used as an anti-parallel diode in power converters, replacing typical JBS diodes?
Yes, I mean, that is the point of us making it such for this particular curve that we showed here. Whether end customers are going to be comfortable using that is really not something I can answer very definitively because, well, I'm not the system designer. But for them to offer such a capability, we believe is important because, you know, once you build it, they will come. And we do believe that it is possible that the third quadrant operation can help in the synchronous rectifier mode, even for these high voltage devices. You know, and the control mechanisms and so on is something that is a challenging thing for our customers. And yeah, that is something that we would love to work with a university to implement.
Thanks. And the last question is, compared to the IDM model currently used in a U.S. chip competitor, what percentage of a 1200 volt, 20 amp silicon carbide MOSFET chip cost can be reduced with your fabless model?
Oh, so not even sure which slide I should point to here. We do believe that the cost benefits of making there are cost benefits to using the foundry model. For example, if you look at the costs that silicon foundries, 6-inch foundries, the cost structure of the 6-inch foundries at the moment, they are so low that it would be very obvious that someone who is setting up their own vertically integrated model would have a hard time competing with an established depreciated 6-inch foundry. Also, we do believe, so in terms of, as far as cost structure is concerned, there are a lot of things that go into the cost structure. Of course, the obvious ones are the materials cost, the foundry costs, and you know, to some extent, the packaging costs. But the other aspects which are underappreciated at this point are things like yields, things like manufacturability, things like you know, capacity and utilization. And we believe that the foundry model, in fact, offers some very strong, compelling arguments for enhancing those aspects of it. And those are, you know, at this point, we believe a pretty big headache for a lot of IDMs. That's our estimate, but maybe I can be educated by the IDMs themselves of otherwise. But our cost structure at this point is competitive, and it's getting even more competitive as compared to the market prices. We are not having to get into a situation where we are not able to offer competitive products at this stage using our model.
Okay, we have a couple more questions that were just added. How do you mitigate stray capacitance and or partial discharge in your MOSFETs?
Okay, as I had mentioned, the MOSFETs are not yet fully released. We are working on such aspects of it right now. You know, there are certainly challenges, as the person who asked the question recognizes. Yes, we are working both internally and with a couple of lead customers in handling those questions. So hopefully in a year I can answer that question a lot better. Sorry about that.
Okay, and the last question now. In your view, what would be the ideal frequency to switch silicon carbide devicing, assuming magnetics and parasitics and EMI comply?
So that depends very heavily on the application. And frankly speaking, you know, we have seen devices being used for, you know, the conventional things like solar inverters and onboard chargers and, you know, battery management systems. But frankly, there are a very, very wide range of people who are using these devices. So it really depends on what the end customer is looking for. For example, on one extreme, I will say there are the circuit breaker applications. Circuit breaker applications, they don't care about switching speed at all, and yet they find the low RDSon of silicon carbide MOSFETs to be very compelling for them to use silicon carbide as compared to silicon devices. On the other extreme are people who are looking to replace, you know, RF devices, and I don't mean the gigahertz type applications. I'm talking about 13.56 megahertz applications where they're using in some medical applications and also for some of these, you know, plasma type application, induction heating kind of applications. So what is the compelling argument? One of the things I always say is that if your application does not require switching at more than 15 kilohertz and switching voltage of at least 650 volts, then you probably don't need silicon carbide, unless, of course, your temperature is more than 200 degrees C or 175 degrees C. Where are typical applications? What frequency are they typically being used? We are finding that for the lower power levels, let's say less than 10 kilowatts, I would hazard a guess that it is in the range of 150 to 200 kilohertz. And on the higher power sides, it's more on the less than 100 kilohertz or so 75 to 100 kilohertz. Of course, there are applications which are using these devices even at 20, 30 kilowatts at 150 to 200 kilohertz. But if I have to pick a median, it would be somewhere in those ranges, around 75 for more than 10 kilowatts and around 150 to 200 kilohertz for less than 10 kilowatts.
Okay, we have one final question. What is the maximum gate oxide field that your design allows?
So we design our devices to not exceed 3.5 megavolts per centimeter, and that is our present generation of devices.
Okay. Any final questions? Any final remarks, Ranbir?
No, I think those are really good questions. I wish I could answer some of them better, but I do very much appreciate the opportunity here.
Okay, thank you very much again for your time, for preparation and an excellent presentation. And thank you all for joining us today. This is our last webinar for the year, and we'll begin again at the beginning of 19. So thanks, everyone, and have a great day.
Thank you.
Bye.